Welcome to Metal Casting Lecture Series by Professor Joyjeet Ghose. This is the 15th lecture of a series of lectures. This lecture will be on carbon dioxide molding, shell molding and investment casting. So, do not miss and watch the full video. For the next video in the lecture series, please click the suggested video link above. You may also click on the playlist at end of the video to access all the videos. Please subscribe this channel and yes, do not forget to like and share. Also click on the bell icon to receive instant information of new videos uploaded. Thank you.
Hello friends, welcome to this lecture 15 of a series of lecture on metal casting. In the previous 14 lectures I have discussed about sand casting, and in next few lectures I'll be covering the other casting processes. So in this lecture we'll be discussing about carbon dioxide molding, cell molding and investment casting. So these three casting processes will be discussed in this lecture. So let's start. We'll start with carbon dioxide molding. A carbon dioxide molding is basically a process of hardening a normal sand casting mold. So how it is done we'll see. So as I have said, the process is basically a hardening process for molds and for cores. The principle of working of CO2 process is based on the fact that if CO2 gas is passed through a sand which contains sodium silicate in certain percentage, the sand becomes, as CO2 is passed, the sand becomes extremely hard and bonded, strongly bonded, and because the sodium silicate becomes a stiff gel. And this gel is responsible for giving the strength to the mold. So we have a better strength of the mold when you are molding with carbon dioxide and silica gel, sodium silicate. So here you have the sodium silicate with water molecules. When gas carbon dioxide is passed, we get this sodium carbonate plus the silica gel. This is called the silica gel, having certain numbers of water molecule. So the ratio of the sodium silicate in the process is called this sodium oxide plus the silica gel, where the ratio of the total alkalinity Na2 to the soluble silica is called the mass ratio, and in this process the mass ratio should vary from 2.1 to 2.3, and the silica oxide obtained by this from this reaction contains certain number of water molecules and is called silica gel. This gel is responsible for giving the necessary strength to the mold. So this actually gives the strength to the mold. So basically the sand that we'll be using should be free from clay, because we don't want the bentonite, the binder in this process, and it should contain less moisture. So with only 3 to 5% of sodium silicate, we'll be able to get the binding of the sand using carbon dioxide. So the rest of the process is similar. We should be adding the additives as is required, like coal powder, coal flour, seed, coal, dextrin, etc. to improve certain properties. The suitable sand mixture is entire thing is mixed in a muller and then placed in a flask or in core box as is required, and the process of mixing and packing is completed. CO2 is forced through the mold under certain pressure for a predetermined period of time. So the reaction takes place in the early stage of gasification, and the compressive strength of the sand reaches a maximum value when a certain critical amount of gas is passed. The gassing can be carried out by a probe having a number of holes at the base, and the flow rate of this CO2 gas depends on the depth of penetration desired. So this is the basically process of hardening the mold. The rest of the process is as similar as that of sand casting, as I have discussed earlier. So what are the advantage of this process? In the first process of hardening the mold, and the removing of the pattern is easier since the mold may be hardened before the withdrawal of the pattern. Accurate casting with sub corners can be obtained. Surface finish of the casting is better compared to sand casting. Semi-skilled labor can be used. Reduces the machining allowances, but obviously it has certain limitations also. The collapsibility, because the sand mold becomes hard, the collapsibility is an issue. And of course, as the silica gel is there in the sand, so reclaiming of the sand is difficult, and the bench life of the sand is much shorter. So applications: producing of casting of valves, pumps, compressor, machine tools, railway components, engine parts, etc., etc. So this is all about carbon dioxide molding. So we move to cell molding process. let me show you a figure then. Okay, so let's start here. So with this figure I can explain the cell molding process. So in cell molding process we use dry silica sand. The sand that we'll be using is a dry silica sand, or it can be a zircon sand, or it can be a mixture of dry silica sand or zircon sand, whatever it is. Okay, mixed with certain additives. The sand is mixed with certain additives to improve certain properties. And also the sand is mixed with certain amount of lubricants like zinc stearate or calcium stearate. The additives are basically coal dust, manganese dioxide, calcium carbonate, manganese silicofluoride, ammonium perfluoride, etc. Some lubricants are also added to increase the flow rate of sand. This is calcium stearate and zinc stearate. And the sand is also mixed with a phenolic resin, which is basically a phenol formaldehyde, and this phenol formaldehyde is used to improve the surface finish and avoid thermal cracking. And this phenolic resin, this phenol formaldehyde, it undergoes thermosetting and becomes stiff and gives and helps in formation of the cell. So here the sand mixed with phenol formaldehyde mixed with certain kind of catalyst called hexa. This hexa catalyst is also important in sand molding, and the other additives like manganese, like coal dust, like iron oxide, and zinc stearate or calcium stearate, all these are added and mixed in a molar, and the sand is prepared. Okay, now the sand is kept in a dump box. This type of box is called dump box. So in this dump box, a heated metal is fitted. The metal pattern, a heated metal pattern. We use a metal pattern in cell molding. So it's costly compared to that of the wooden pattern. So we use a metal pattern here which is heated. And this metal pattern is fixed in the dump box, and the dump box is then turned over like this in this figure. So when it's turned over, the sand that is there in the bottom of the dump box will fall on the heated metal pattern. And this metal pattern is heated to around 250 to 200 degree, 250 degree centigrade. So the phenol formaldehyde, which is there as a resin in the sand, which is near to the heated metal pattern, will undergo thermosetting, and a sand cell will form around the pattern surface. And it is kept for a certain period of time, let's say for 30 seconds or for 60 seconds. When suitable cell thickness is formed, then it is overturned. So loose sand will fall, and the sand where thermosetting resin, the phenol formaldehyde has undergone thermosetting, a cell will be formed following the profile of the pattern. Then slowly this will be ejected. This will be ejected by ejector pin. The cell will be ejected like this, and then actually it is again heated to undergo complete thermosetting, then for complete curing rather. So when it is completely cured, number of normally 2 such pieces will be joined by adhesives and placed in a flask, and metal is poured. So the metal will enter into this mold cavity, and it will solidify and will break the cell and take out the casting. So this is essentially a multiple use pattern, just like sand casting, because this metal pattern will be using multiple times, but the mold, that is the cell mold that we formed, will be used single time, just like sand casting. So this also comes under classification under sand casting, like that. So what is the advantage in comparison with the sand casting? So what is the advantage of that? You can see so thin sections can be cast very easily. Okay, how much resin? Resin is around 4 to 6% by sand by weight, and the catalyst is around 14 to 16%. What is this catalyst? The catalyst is basically a hexamethylene tetramine known as hexa, and this phenol formaldehyde normally undergoes the thermosetting at a temperature around 150 degree centigrade. So there are various ways we can mix the sand, this is called hot coating process, warm coating process, or cold coating process. In hot coating process, is basically expressed due to combined effect of the heat as well as the chemical action of the resin with the catalyst. Once the curing is done, the cured sand is cooled to around 40 to 50 degrees centigrade, so that no lumps are formed. In warm coating process, what happens? The different resin formulations, which is mixed with liquid, is used, and its curing takes place at around 80 degrees centigrade. The process is much simpler compared to that of hot coating, but the quantity of resin consumed is larger in this case. And in cold coating process, sand is first mixed with the catalyst, that is the hexa catalyst, and then the resin is mixed with alcohol and is added to the aggregate. The amount of resin required is highest in this process in comparison to the amount required in hot and warm coating process. So this is the coating process, and phenyl formaldehyde resins that are used, and hexa catalyst, as I have said, is basically hexamethylene tetramine, and certain lubricants are used. As I have said, additives are also used to enhance the surface finish of the casting and to develop the resistance to thermal cracking and distortion. Various additives like coal dust, manganese dioxide, calcium carbonate, ammonium borofluoride, lignin, iron oxide, etc., etc. And also we use certain kind of lubricant so that the flowability of the sand increases. This is basically zinc stearate or calcium stearate. So what are the advantages? Obviously, better surface finish in comparison with sand casting. When I say advantages, I mean advantages in comparison with sand casting. Machining of the casting is reduced because it's much more accurate, and the chances of blowholes or air pockets are reduced because the sand is more permeable compared to the sand in sand casting. The cells can be stored for a long period of time, high dimensional accuracy. The draft of the vertical sides are reduced, and very thin sections can be cast. Permeability of the cell is high, so small amount of sand needs to be used. Mechanization is possible. So these are some of the advantages of cell molding, but it also has certain limitations. Limitations is that we have to use a metal pattern, which is much more costlier, and that cost is justified only when it is used in mass production. And the size also is limited because of the metal metal pattern. So size is also limited here. Highly complicated shapes cannot be produced. More sophisticated equipment is required for handling the hot metal pattern. So high resin cost is also high, and it's not economical for small production runs, obviously, as I have discussed, and relative inflexibilities in getting an risering system. So application includes cylinders, cylinder heads of air-cooled IC engines, which are very, very thin fins, small crankshafts, automotive transmission parts, bevel gears, brake beam, etc. These are only some of the applications of cell molding. Cell molding is very, very popular in automotive industries. Okay, with this we move on to another very important casting process, widely used casting process, and which is a very, very accurate and precise casting process, that is called investment casting or lost wax process. So in this process, this is a beautiful diagram and very colorful in that. In this diagram you can see there is a metal die. This die is specifically made to make wax pattern. So in this die we inject wax pattern under pressure and allow the wax to solidify in the die, and then we take it out. So such number of patterns are made and assembled using a wax center sprue and pouring basin. So it is also made, this is also made of wax, and these are assembled in a tree structure. So once it is assembled in a tree structure, it can be glued or it can be fixed with wires, whatever it is, can be done manually. And once this is done, the tree structure is made, then it is dipped in a refractory slurry, normally ceramic slurry. So it is dipped and it is dried, dipped and dried, dipped and dried till specific thickness is obtained, and then it is dipped in a stucco coating, where basically a fine silica, it is basically a fine silica gel is used to coat it again dipped, again dried. So once this is done, the coating is done, this is inverted and it is heated to around 100 degree or more than that, to 100 degrees centigrade, so that the wax melts and comes out. So when the wax melts and comes out, we left with a cell, which is basically our investment material. Then before pouring, we heat it to around 1000 degrees centigrade, and then we can pour the molten metal. So this is a method which even Egyptians 3000 years ago used to use this method for making jewelries. So this is highly suitable for making small components which are very, very precise. Now the beauty of the process is that here we are not removing the pattern. Rather, we are melting the pattern and taking out. Now, this enables us to go for complex shape of the casting. Now, we are limited in sand casting in a sense because to the complexity of the pattern which can be taken out. The pattern has to be taken out, obviously, and that limits the complexity of the casting. Now, here we are not taking out the pattern, rather we are melting the pattern inside the cell and we are taking it out. So this enables us to go for highly complicated shapes. So that is the beauty of investment casting. So what are the advantages? High dimensional accuracy, very smooth surface, can be achieved. Extremely thin sections to the extent of 0.7 mm can be cast successfully. Complex shapes, as I have said, suitable for mass production, can be automated. Limitations, the process is normally limited to the size. More expensive because you are using ceramic material, production rate is slow. Application, turbine plates, parts of automobile, waveguides, radars, triggers of firearms, stainless steel valve bodies, etc., etc. Okay, so in today's lecture we have discussed 3 different types of casting processes, that is CO2 molding, cell molding, and investment casting. I hope you have liked this video. In case of any confusion, any doubt, please feel free to contact me. Thank you for watching this video.